Happy Monday, everybody. Today I want to talk to you guys about a technique called thin layer chromatography. If we think about the word thin layer chromatography, chroma comes from the Greek word color. Ography is sort of the field of study of something. So we know that it has something to do with color. Well, one of the things that I've observed with commercial and amateur mushroom growers is they're often focused on breeding the most desirable physical phenotypes, physical characteristics of the mushrooms. But there are a lot of mushroom growers that are selling gourmet and edible mushrooms because of their medicinal properties. Cordyceps have things like cordycepin in it, which is shown to improve oxygen uptake in red blood cells. But there doesn't seem to be a great way for mushroom growers to quantify those valuable and medicinal compounds inside the mushrooms. So thin layer chromatography can aid in that. And this is a project I'm working on to potentially develop a kit that's low cost and anyone could use to determine what compounds are present in the mushrooms that they're growing and in what quantities potentially. And that should greatly improve the type of breeding that's done that will yield improved quantities of those valuable compounds. So with thin layer chromatography, we basically have a glass jar, which acts as our developing chamber, a solvent on the bottom, which we call our mobile phase, and then we have our stationary phase, which is going to be, in our case, this experiment that we're about to run is a thin piece of paper. This is a chromatography paper. It's cellulose and it's quite polar. So we're going to be taking some ash leaf, which I have from a tree that I received outside, crushing it up, and then putting it in some solvent, which happens to be some acetone, nail polish remover. And we're going to be, what's TLC? Like, what's the point of it? Well, it actually separates out the compounds that are present within the particular subject matter here. In our case, we're going to be taking a leaf extract, separating out its constituent components, and that way we can actually see what's inside of that extract. Well, how do we know what's in there? Well, it turns out that different compounds, because they have different polarity and salinity, polarity and solubility, will travel at varying distances up the stationary phase, which is this piece of paper here. And we call that measurement RF, or retardation factor, where it's basically the difference, it's a ratio of how far the solvent travels up the paper versus how much, actually it's how far the individual compounds, so let's say we're using a leaf and chlorophyll's here, we can do a ratio of how far did the chlorophyll go up versus how far the solvent front ended up being. This is basically where did the solvent stop getting soaked up by the mobile phase. And this is known for most compounds, most organic compounds. So cordycepin or terpenes or even psilocybin have published values where you could use TLC to detect their presence, and then eventually we're working on a way to actually quantify that. So let's go ahead and do that. This is basically going to be recreating this experiment here right now. So I'll tell you what I'm going to be using. I told you about the paper chromatography strips, pretty easy to get a hold of. I have a strip right here. And note that I try not to touch it too much because I don't want the oils from my fingers to be soaked in by the paper and interfere with the results of the tests. I have my developing chamber, which is just a mason jar, some acetone. I don't have a mortar and pestle. Instead, I've taken some leaves and I put them in a coffee grounder, and we'll go ahead and just give this another quick whirl right now. And we basically want to grind it enough that we can take some of the natural extract of the leaves, the natural oils and stuff, and be able to transfer that to this paper. The other thing I'm going to do is I'm going to mark the origin on the paper. And the origin is an important demarcation. It's this little line right here in the paper. So I'm going to mark this 5 millimeters up from the bottom of the paper. And note that my solvent, the mobile phase, of TLC is going to actually be in the jar just below that. You actually don't want it to, you basically want the solvent to be soaked up by the paper due to the capillary effect and to reach the solvent. And then as it hits this extract here and begins to climb up here, the different compounds within here are going to separate. And as they separate, they're going to create different colored marks on the paper. So let's do that. So we're going to take our piece of paper here. I'm going to mark a 5 millimeter mark as my origin. And I've done that. Now I'll take my little tweezers, see if I can show that to you. You can kind of see a little marking right there. Now I'm going to take a little bit of this extract here, and I am going to take this little pinch, and I'm going to attempt to just put it on the paper and push it in, because I want to see if I can get as much of the oil, the extract, from that little bit into the paper. Kick off some of the excess here. Now let me show you the paper. So you see that I've taken some of that leaf, that ash tree leaf extract, and I just took my tweezers and I kind of just smooshed it in here. Okay, now we're ready to take our developing jar, and we are just going to put just a little bit of acetone. We really don't need much, because again, we don't want it to pass the origin. We want it to be soaked up by the origin. So we've got some acetone, and just want to do a quick check here again, and I would rather have less, because I have it's very easy to do too much. And in the bottom of this jar, I mean, it's not a great jar because it's not flat. It's actually deeper on the edges, which happens to be where the paper sits. And then the paper's going to go inside of here, and immediately will start to be sucked up by the paper. So let me make sure I've got enough in here. And it looks like I do. All right, so now it is working, and I'm going to put the lid on so my solvent doesn't evaporate. And you can kind of already see what's happening is that this solvent, the solvent front is slowly rising. In fact, if you look really, I don't know if you can see it very closely, you can already start to see some green there. I'm going to set it down because I want to make sure that I don't tilt it such that the acetone covers up the sample, because that really will impede its ability to work properly. But notice the solvent front, it continues to rise. And what we're going to do is we're going to wait for the solvent front to stop. So once it stops, we can actually take this paper out and get a better look at the different compounds that have been separated out. So imagine if you could zoom into the molecular level, that acetone was sucked up by this paper, and it hit the oils in the extract, and the extract has a lot of different compounds in it, like chlorophyll and different kinds of chlorophyll, and anthocyanin and carotenoids and all kinds of things that frankly I don't know a lot about, but because they have different solubility and because they have different polarity, they are being stretched, and some of them will attach themselves to the mobile phase, which is the strip, quite strongly, and so they don't travel as high up. And other ones, they're not quite as polar, so they can get pulled up quite easily. And so here we go, and I can already start to see some results, but it looks like it's still traveling here. So we give it a little bit more time, and we just see we're almost looks like it's almost done moving up. Quite interesting indeed what I'm noticing, and it's kind of hard to tell in the video. Let's see if I can get it a little bit closer. You can actually see the solvent front where there's that really pronounced green line there. Yep. And just make sure it's not moving up anymore. And it doesn't look like it. So I'm going to take this out. So let's take a look at this. What do we notice? We notice that our sample's right here, but we see a gradient here. We actually see a very strong demarcation here, which is the solvent front, and then we see this gradient pattern here. Now, because of this technique in this paper, which is somewhat imprecise, somewhat not very precise, I should say, it's going to be a little bit difficult to see all the distinguishing compounds that are in this particular paper, but we can at least see understand the concept and the idea of it. This is the solvent front, this is the origin, and if we were to look at this under a black light, we might actually see more distinguishing features. And we let this dry a little bit more, and as we let it dry, let's see if I can air it out a little bit. Can really get a sense of kind of what it looks like. So now, to calculate the retardation factor, which is, retardation, how slow or fast is it moving up here? If we were to want to try to determine what this particular compound is that caused this really dark green spot here, we would measure the total distance that this particular compound traveled divided by the total amount that the mobile phase, the solvent, traveled up here. Now, I probably made a mistake here because this demarcation is darkest right at the solvent front. So it would, have an RF factor of 1. And I don't know that tells us a whole lot. But that's the central idea of this. So this is an interesting way that you can take a compound, separate all of its constituent components, and with other compounds and more purified techniques, there will be more differentiation between, there might be a dot here, there might be a dot here, but you can use this to determine what compounds make up your subject down here, which has a word for it, analyte. This is called your analyte. You can look at the different compounds that make up that analyte, and so I think that's pretty cool, and this is something that I think would be really interesting and useful for the mushroom growing community if they could actually know. They can actually know what compounds are in the mushrooms that they're growing, quantify them, and then use that in their breeding. Right now, everybody kind of just flies blind, and that doesn't necessarily equate to mushrooms that yield the highest percentage of the various compounds. So anyway, that's TLC, thin layer chromatography. Pretty cool.